Can you hear my voice? Okay, thank you. Okay, we are going to continue our lecture on the new subtopic. Okay, for this chapter number 4, compressible flow. Okay, but before that, we are going to do maybe a few examples about the choke flow. Okay, I think in last class, before we end our class last week, so I have explained to you about the choke flow. Okay, choke flow. So choke flow is basically the conditions. Okay, where you only have convergent nozzles. You don't have any divergence sections. And are you able to get the supersonic flow? Okay, are you able to reach, okay, Mach number is equal to 1 at the end of the convergence nozzles? Okay, so basically when you reach Mach number is equal to 1 at the ends of your convergent nozzles, it means that the flow is choked. Okay, if you reach Mach number is equal to 1 at the end of these convergent nozzles, it means that the flow is choked. Okay, so what will happen if the flow is choked? Okay, so when Mach number is equal to 1, the flow is choked, it means that the mass flow rate is maximum. Okay, the mass flow rate is maximum. If you further reduce the pressure at the back, okay, if you further reduce the pressure at this receiver, so the Mach number will remains equal to 1, and the mass flow rates also will not increase. Okay, if you further reduce the pressure, it means that your pressure ratio will be lower. It means that it will not further increase the mass flux. Okay, so the very important points that you have to understand here is, if the flow is choked, Mach number reach once, it means that the mass flux is already maximum. Okay, so that is the key points lah. Okay, let us look at these examples. A converging nozzle with an exit diameter of 2 centimeter is attached to the reservoir. Reservoir is in the front here lah. Maintained at 25 degrees C and 200 kPa absolutes. Okay, so the temperature and pressure at this reservoir is 25 degrees C and 200 kilopascal absolutes. So the question is, determine the mass flux of the air if the pressure at receiver is the is here lah, okay, the back pressure. Determine the mass flux of the air. Okay, what will be the mass flux m dots go through these converging nozzles if the pressure at receiver is 100 kilopascal absolutes. Okay, and B, if the pressure at receiver is 130 kilopascal absolutes. Okay, so that is the questions. Okay, now first we have to determine, okay, whether the flow is choked or not. Okay, so what will be the relations, okay, between the pressure at the receiver and at the reservoir? Okay, so you have to understand. So in order to get Mach number is equal to 1, okay, we want to check whether the flow is choked or not. Okay, so when the flow is choked, Mach number is equal to 1. Okay, Mach number is equal to 1. at this area. And when Mach number is equal to 1, the pressure ratio will be equal to 0.5283. Am I right? Or okay, so this one I think you have to refer back, okay, to my lecture notes for the equations, okay, the relationship between any point inside the converging nozzle with reservoir, and then when Mach number is equal to 1, then you will get this kind of values, okay, 0.5283. So this is the pressure ratio when Mach number is equal to 1. Okay, so now we know that the pressure at reservoir is 200 kilopascal. Okay, so what should be, okay, the pressure at receiver in order to check whether the flow is choked or not? Okay, so pressure will be simply equal to 0.5283 multiplied by the P naught lah. P naught is 200 kPa. Okay, so what will be the pressure? What is my... Okay, 0.5283 times 200. Okay, so you get 105.66 kPa. Okay, it's on 105.66 kPa. Okay, so this is the pressure at reservoir. Should be when you want to have Mach number is equal to 1 at the throat area. Okay, so this is the pressure. Okay, so what does it mean? In order to get Mach number is equal to 1 at this throat, at the end of this nozzle, the pressure at receiver must be less than 105. Okay, I hope you understand my statements. Okay, in order to get Mach number is equal to 1 at the end of these converging nozzles, pressure at receiver must be less than 105.66. Okay, so let us look at this question A. Okay, the pressure at receiver is 100 kPa. Okay, so 100 kPa is less than 105.66. So it means that the Mach number here will be equal to 1. Okay, I repeat once again. For question A, the pressure at receiver is 100 kilopascal, and 100 kilopascal is less than 105.66 kPa. So it means that the flow is choked and Mach number is equal to 1. Okay, so for case A, Mach number is equal to 1 and the flow is choked. Okay, and for the second case B, the pressure at receiver is 130 kPa. Okay, 130 kPa is greater than 105. So it means that the flow is not choked and Mach number is not equal to 1. It is less than 1. It must less than 1. Okay, because the pressure ratio will be lower than 0.5283. So it is not choked. Okay. All right. So that is the idea. So the question is determine the mass flux. Okay, determine the mass flux. So for question A, okay, what is the equations to determine the mass flux? So there are, I think the question, sorry, the equation is quite long. Okay, so you can calculate lah. Okay, but I think this is sorry, m dot is equal to P naught multiplied by K over R T naught multiplied by the what is the equations? Uh, wait, Okay, multiply by the Mach number, multiply by the area, and then multiply by Mach number square over 2, k minus 1 plus 1 to the power of k plus 1 over 2, 1 minus k. Okay, so this is how you determine the mass flux. Okay, so I think everything is been given. So, okay, you know the P naught, the K is 1.4, R is the gas constant, T naught is already, this is given. So, okay, 25 degrees C. So, Mach number is equal to 1, okay, because the flow is choked, area is been given, diameter here is 2 centimeter. Okay, Mach number is equal to 1, and so on. Okay, so you will get the answer. Okay, this is the kilogram per second. Okay, all right. Okay, that is for the case number 1. So for case number 2, we know that the flow is not choked. Okay, the flow is not choked because the pressure at the receiver is greater than 105. It means that the pressure ratio here is less than 0.5283. Okay, so the flow is not choked. It means that it's not reached the supersonic. Okay, it is remain in subsonic. Okay, Mach number is less than 1. So for this case, we have to determine, okay, what would be the Mach number first. Okay, what is the Mach number? We know that the Mach number is less than 1, but we have to know exactly what would be the Mach number. Okay, so how to find the Mach number? Okay, we can use the pressure ratio lah. Okay, use the equations. We know the pressure at the back here is 130, so we can use this kind of equation lah. Okay, you can refer back to my lecture notes. P over P naught is m square over 2, k minus 1 plus 1 to the power of k over k minus 1. Okay, so we know all of this. P naught is 200 kPa. So the pressure at receiver is 130. Mach number is the unknown. K is 1.4. So if you substitute all of the values, so at the end you will get Mach number is around 0.8092. Okay, so it is subsonic lah. Okay, so once you determine the Mach number, then you use the same equations here, okay, to get what will be the mass flux lah. Okay, you substitute Mach number is equal to 0.8, then you will get the mass flux. Okay. Okay, any questions? No questions? All right. So I believe that everyone understands this about the choke flow. Let us try the next examples. Okay. So for this case, okay, air flow from a converging nozzles. Okay, so we have a converging nozzles here attached to the reservoir. Okay, so this is the reservoir lah. With temperature at the reservoir is 10 degrees C. So the question is, what pressure at reservoir is necessary, okay, to just cause the M exit is equal to 1. Okay, ME stand for the Mach number at the exit lah. Okay, so you know here the Mach number at the exit is equal to 1. If the 6 centimeter diameter nozzle exits to atmospheric pressure, okay, so it exits to this atmospheric pressure, PATMs, absolute. Okay, we're talking about absolute. In compressible flow, the pressure it's not normally. You must also always consider that the pressure is in absolute. Okay, not gauge pressure. Okay, calculate the mass flux. Okay, for these conditions. Okay, so here is PATM lah. Okay, about 101 kPa. Absolutes. Okay, so what will be the pressure? Okay, at this reservoir in order to reach Mach number is equal to 1 at this exit. Okay, everyone, please try to do this. calculate the mass flux. Okay, find the pressure at reservoir first, and then find the mass flux. Okay, anyone? What will be the answer? Give me the pressure at reservoir first.
191.179 kilopascal.
Okay, 191.7 kilopascal.
191.179.
One, okay. It's okay. Thank you. That is the correct answer. Okay. So, okay, your answer is quite different because I use 101.3. Okay, but it's okay. Okay, at least you know what will be the PATMs here. So as I mentioned, as I stated earlier, that in order to get the Mach number is equal to 1, so the pressure ratio, okay, should be 0.5283. So for this case, you want to find what will be the pressure at reservoir. So it is simply 101 kPa divided by 0.5283. So you will get around 191. 1.1. So I use 101.3. So I get 191.75 kPa. Okay, doesn't matter. So this should be the pressure at reservoir. Okay, in order to reach Mach number is equal to 1 at the exit of your convergent nozzles. Okay, so now once you have determined the P notes, so you can simply calculate the mass flux lah. Okay, so you can use this equation back. Okay, so these equations, so the Mach number is equal to 1, area you know, and so on lah. Okay, so you already determined the P naught and so on. And uh, if you want to know basically the m dots, okay, the mass flow rates, okay, you can also uh, use this kind of equation actually. Okay, it's not a different equation actually. This equation is basically derived from the relationships, okay, the pressure ratio as well as the temperature ratio. Okay, if you have a textbook, I think I'm not sure whether our books is showing the derivation of these equations, but If you have other like a Porter textbook, they show okay the derivation how they get this kind of equations. Okay, so it's basically derived from this kind of continuity equations. So what is rho? Rho is basically pressure divided by RT. Okay, this is the ideal gas relationships. So times the velocity. So what is the velocity? Mach number is equal to velocity divided by c. So this is simply krt lah. Okay. So the velocity here is the Mach number uh, times krt times the area. Okay. So you can also use this kind of equation as well. Okay. But here I think you have to find the temperature at exit. Okay, you also need to find what will be, so pressure here is the pressure at exits, temperature at exit. So you have to find lah, okay, what will be the temperature at exits. Then you can use this kind of equation. So my number is equal to 1 krt. T is also the temperature at exits, area at exits. Okay, you have a 6 cm here. So you can also use this kind of equation as well. Okay. All right, so that's all about the isentropic flow. Okay, so we have covered a lot of things. Okay, speed of sounds, Mach cone, and then isentropic flow. We have learned about the relationships, okay, between the velocity and area at supersonic and subsonic flow. Okay, that is very important. That is where the CD nozzles is coming from. Okay, the idea of designing CD nozzle is coming from. Okay, and then the last one will be the choke flow lah. Okay, so that's all about this isentropic flow. Okay, and this topic will be covered in your test too. Okay, in your test. Okay, so let us continue our lecture on the next subtopic. Okay, the next subtopic will be about uh, okay. So the topic is shock wave. Okay, the shock wave. Okay, so this is, I think it's very simple one. Okay, and it is going to be covered in your final exam. Okay, shock wave will be covered in your final exam. So let us look at what is the shock wave. This is the definition. Okay, the shock wave is a large amplitude disturbance. It can be oriented normal to the flow or at oblique angle. Okay, so I think in our syllabus we only cover the normal shock wave. Okay, not oblique shock wave. So the property changes across the shock wave occur over an extremely short of distance. Okay, with a thickness only 10 to the power of minus 4 mm. So this is basically the thickness of the shock wave lah. Okay, since the thickness of shock wave is very thin, it can be considered as zero thickness discontinuity. The presence of shock wave results in drastic increase in pressure, temperature, and entropy. Okay, this is based on second law of thermodynamics. Okay, this is the very important point. Okay, I repeat once again. The presence of shock wave results in a drastic increase in pressure, temperature, and entropy. Okay, it means that if the flow cross the shock wave, the pressure will be suddenly increased, the temperature will also increase, as well as the entropy will also increase. Okay, so I think the most significant difference, okay, between the shock wave and isentropic flow is about the entropy. Okay, isentropic flow, we know that for the isentropic flow, there is no changes in entropy. Okay, delta S is equal to zero. Okay, that is for the isentropic flow. Okay, but for the shock wave, delta S is not equal to zero. There is a changes in entropy. And then how it is formed when the pressure front move at a supersonic speed and push on to the surrounding air. It is a propagating disturbance that move faster than the local speed of sound of the medians. Okay, that is the definition lah. And this is the difference between the sound wave and the shock wave. Okay, I think you can read by your own lah. Okay, and this is the example of shockwave in our real life as well as in engineering applications. Okay, water hammer in pipelines. Water hammer is a phenomenon that occurs when a fluid in motion is forced to stop or change direction directly. Change direction suddenly, creating a pressure wave. Okay, shockwave in the pipelines, wind tunnel for supersonics, high pressure fuel injection systems, so on. Okay, okay. So what is shockwave? Okay, visually, this is the shockwave. Okay, when the object is moving, when the object is moving at supersonic flow, okay, it must move at supersonic flow. Then the shockwave will appear. Okay, the shock wave will forms. Okay, for example, on the left sides, okay, the image on the left is basically like a bullet. Okay, this is basically like a bullet. Okay, so when the bullet is traveling at the supersonic speeds, okay, so it will form like you can see like a line. Okay, like a line in the fronts of the object. So this is what we call as a shock wave. Okay, so this is what we call as the shock wave. Okay, and on the right side here, so this is the oblique shock wave lah. You have a certain angle. Okay, you have a certain angles. This is like a what we call as a oblique shock wave. Okay, on the left side here, so this is the bullets. I think there are many videos that you can see in the internet. Okay, if you have a time, so you can Googles and types search on the YouTube maybe what is the shockwave. Okay, see, I think there are many experiments that have been done. The what we call they use like pistols, and then they release the bullets, and then they capture. Okay, they capture the videos and they do the slow motions, and they see clearly, okay, the formations of this normal shockwave. Okay, that is very interesting to see. Okay, so basically this topic is very for me is very easy. Okay, what you need to do is normally we have to calculate, or we have to analyze what is happening to the flow properties before the shock wave and after the shock wave. Okay, means what will happens at the upstreams regions, I mean before the shock wave, and what will happen to the flow properties after the shock wave. Okay, what will happen to the pressure, what will happen to the temperature, what will happen to the entropy, and so on. Okay, okay, so let us analyze, okay, on our shock wave here. Okay, so let's say we have a shock wave traveling at the velocity of v1. Okay, nampak this one kan. Okay, so this is the shock wave. Okay, for example, this is the shock wave. Okay, that is traveling at the velocity v1. Of course, okay, there should be a supersonic flow lah. Okay, so in order to get our analysis much more easier, rather than in sorry uh, rather than analyzing the moving shock wave, let us make it fixed, and we have the free stream velocity at the same speed of v1. Okay, so rather than analyzing the moving shock wave, let us put the shock wave in a fixed control volumes, and let us hit the shock wave with the same flow, okay, the same velocity that the shock wave is traveling. Okay, so this is going to be the diagram lah. Okay, I hope you understand. Okay, this the difference between these two. Okay, so the left one is basically the shock wave is moving at the velocity v1, and it's quite difficult for us to analyze. So let us put the shock wave in a fixed control volume, and let us hit the shock wave with a flow, okay, with a velocity v1, okay, the same velocity. So on the left side here, it is considered as upstreams, okay. So this should be in supersonic regions, and after the shock wave will be the subsonic regions, okay, and this is the shock wave lah, okay. So what we are going to do is we just need to determine what will be the flow properties before the shock wave here and after the shock wave. And these are the derivations. I think you can read by your own. Right? From the continuity equations, we assume there is no work done, no heat transfer, and so on. Okay, and at the end, what we get is the relationships, okay, between the flow properties after the shock wave and before the shock wave. Okay, so at the ends, okay, so this is the relationships. Okay, the Mach number 2 square, m2 square is the Mach number after the shock wave, is equal to m1 square plus 5 over 7 m1 square minus 1. So this is the relationships. And the pressure ratio becomes this equation lah. Okay, so this is basically when we assume that the flow is air, okay, where K is equal to 1.4, and then we substitute K 1.4, then we get this kind of equation lah. Okay, if not, if you use different types of gases, so you will need to have different types of K lah. Okay, so you have to use this kind of equation lah, not the one that I enclosed with the red line here. Okay, so this is the T1 T2 over T1 here, and this is the P2 over P1, and this is M2 square lah, M2 over 1. Okay, so this one is also very important. Okay, and if the fluid is air, so it is simplified to this equation lah. Okay, so I hope you understand. Okay, pressure, temperature, and so on. Okay, so from these three relationships, it can be observed from three different conditions. Okay, so if M1, which is the Mach number before the shock wave, is equal to M2, is equal to 1, the pressure ratio will be equal to 1. Okay, it means that P2 is equal to P1. It represents no discontinuity and shock wave does not exist. Okay, so if M1 is equal to M2, which is equal to 1, even it is supersonic, okay, but the pressure ratio is equal, okay, which is equal to 1. So it means that no shock wave, okay, shock wave does not exist. For the case number 2, if Mach number 1 is greater than 1, which is supersonics, and Mach number 2 is less than 1, which is subsonic, it means that normal shock wave occurs and converts supersonic to subsonic. Okay, so this is the conditions, okay, in order to prove that the shock wave exists. Okay, Mach number 1 must be supersonic. Okay, here, Mach number 1 here, before the shock wave must be supersonic, and Mach number 2 must be subsonic. Okay, so that is the conditions that must be fulfilled in order to prove that the shock wave exists. Okay, and the last one will be if Mach number 1 is less than 1, which is subsonic, and Mach number 2 is supersonic, it means that normal shock wave converts subsonic to supersonics. Okay, but according to second law of thermodynamics, these transitions results in entropy decreases, which is impossible to occur. Okay, therefore this condition will not going to happen. Okay, so the third condition is impossible to happen. Okay, it means that Mach number 1 subsonic to supersonic, that is not possible to happen lah. Okay, so you only need to know that the second condition here, Mach number 1 must be supersonic, and Mach number 2 is subsonic. Then only the between these two region is considered that the existence of the shockwave. Okay, the existence of the shockwave. So that is the conditions. Okay, so let us look at these examples. Okay, a normal shock wave pass through a stagnant air at 15 degrees C and at an atmospheric pressure of 82 kPa with a speed of 453 meter per second. Okay, find the temperature and pressure downstream of the shock wave. Okay, so this is the upstream before the shock wave, and this is downstream after the shock wave. Okay, find the temperature and pressure downstream of the shock wave. Okay, after the shock wave lah, by using equation and shock wave table. Okay, so for the shock wave also there is a table. You also have two options in solving this kind of problems, either by using equations, these equations, or you can also use a table. Okay, you can also use a table. Okay, so it's very simple actually. So we know that before the shock wave, pressure is 82, temperature is 15, and velocity is 453 meter per second. So what we need to do is we have to find first. Okay, the first question is using equation. Okay, using equations. So we have to find what would be the Mach number first. Okay, so Mach number 1 V over C. Okay, we know the velocity is 453. Then we get the Mach number 1 is 1.33. Okay, so it is valid. It fulfills the conditions. Okay, where Mach number 1 before the shock wave must be supersonic. Okay, Mach number must be greater than 1. Okay, so you can just simply use the equation lah. P2 over P1, then you get the P2 lah. Okay, pressure after the shock wave. Similarly, for the temperature, use this equation, then you get T2 is equal to 348. Okay, and this is what will happen. Okay, this is what will happen if you look back, okay, at the definitions or the explanation about the shock wave. Okay, the presence, okay, the fourth point here, the presence of shock wave results in a drastic increase in pressure, temperature. Okay, pressure and temperature. Okay, so look back here. Okay, so the pressure before the shock wave is 82. Sorry, and after the shock wave, it is increased up to 155.56. Okay, here is 82 and P2 is 155.56. Okay, similarly for the temperature, it is 15 degrees C and after the shock wave is 348 Kelvin. Okay, so this is the difference. Okay, this is the difference between the pressure and temperature. Okay, you should be able to draw, okay, this kind of diagram. Okay, TS diagram show, okay, what will be the pressure increase, what will be the temperature increase, and also there is one more parameters here that is missing, which is the entropy. Okay, entropy will also experience drastic increase. Okay, entropy will also experience drastic increase. Okay, so how to determine the delta S entropy? I think there is equations. Wait, I just want to show. Is there any? entropy equations. Right, this one. Okay, the delta S, okay, is equal to Cp ln T2 over T1 minus R ln P2 over P1. Okay, but for the isentropic flow, delta S is equal to zero lah. Okay, but for the short wave, delta S is not equal to zero. Okay, there is a value delta S is greater than zero lah. Okay, so that is how you find the delta S. Okay, so that is the answer of using equations. And then uh, what will happen if we use table? Okay, so I have shared this table with you previously. I think table D1. Okay, table D1 is for the isentropic flow, and if you scroll down, you will have a table D2, okay, which is the normal shock flow table. Okay, it's a bit different with the isentropic flow, where in here you will see there are 5 columns, but I would say that you can simply ignore the last column. Okay, this P02 over P01, I think you can ignore this one because it's not going to be in our syllabus lah. Okay, so you just concentrate on the first 4 columns. So we have a M1 stand for the Mach number before the shock wave. It has to be supersonic. Mach number must always greater than 1. And Mach number 2 is represent the Mach number after the shock wave, and it has to be subsonic. Okay, Mach number must be less than 1. And here you also have the P2 over P1 and T2 over T1 lah. Okay, before the shock wave and after the shock wave. Very simple table actually. Okay, so for this case, we already determined the Mach number is 1.33. Okay, this one we already determined Mach number is 1.33. So look, use this table. Okay, we want to find the pressure and temperature. So 1.33 is here lah. So you have to interpolate, then get the P2, similarly the T1 and T2 as well. Okay, so that is the things. Okay, any question about the shock wave? Everyone, do you have any questions about the shock wave? It's much more simpler, right, compared to the isentropic flow. Okay, so I believe that everyone understands, and then let us try to do the tutorial lah. Okay, let's try to do the tutorials. Okay, everyone, please try to do this example number 1 first. Table, you can refer to the table I have shared in the WhatsApp group previously. So everyone, please try this example number 1. So they give you the pressure, temperature, as well as the velocity before the shock wave. So you have to find what will be the Mach number 1, Mach number 2, pressure. Okay, so these subscripts 1 represent before the shock wave and 2 represent after the shock wave. Okay, so try to use these both methods. Okay, using the equations and also use the table. Okay, everyone, please do. I give you 5 minutes. In order to use the table, I think you have to round your numbers into two decimal places. Okay, because if you look at the tables, for the mark number one, you only have two decimal points. Okay, 1.30, 1.32, 1.34, and so on. Okay. Okay, so for this case, I think you have to show this kind of diagram. Okay, your control volume. Okay, so this is the shock wave. Okay, you have to show this one. So this is the upstream and this is the downstream. So here, before the shock wave, the pressure 80 kPa, temperature is about 10 degrees C, V1 is 1000. Okay, so this kind of things lah. Okay, so you have to show this kind of diagram. Okay, make sure you are able to sketch, okay, this kind of things. So what is, okay, so this is the questions. What is the M1? What is the M2? What is the P2 and temperature as well as the density? Okay, anybody want to share the answer? What is M1? It's very simple, right? Very straightforward. Anyone? What is M1? Dah dapat tak M1? 2.966. Okay, correct. Okay. Uh, Very simple, right? So mark number one is equal to V1 lah. 1 over C. So it is simply 1000 divided by square root of K R T lah. 10 plus 273. Okay. So you will get around 2.966 or maybe 2.97 lah. Okay. So the answer will be a bit plus and minus lah. Okay. So that is your M1. And once you get M1, you can determine the M2. Okay, so use the equation. So m2 square, since this is the air, so you can simply use this equation lah. M1 square plus 5 over 7 m1 square minus 1. Okay, so for this case, you will get m2 around 0.477. Okay, so if you look here, m1 is supersonic, greater than 1, and m2 is subsonic, okay, 0.477, less than 1. So it proved that the shock wave exists. Okay, so once you get m2, so you can directly use equation lah, okay, to find what is the pressure. So you can use these relationships. 2 over P1 is simply 7 1 M1 square minus 1 over 6. Okay, so I give you the answer. P2 is equal to 807.73 kPa. Okay, similarly for T2 over T1, so the equation is a bit long. Times 7 m1 square minus 1 divided by 36. So I give you the answer is about 746.8 kelvins. Okay, so this is the answer. M1, M2, P2, T2, and the last one is the density. Okay, so how to find the density? So you can just use the ideal gas relationship lah. Okay, so P2 is equal to rho RT. So rho 2 is simply P divided by RT2 lah. Okay, we just substitute all the values and we get density is about 3.768 kilogram per meter. So this is the answer. Okay, so you can cross check. Okay, you can cross check your answer. Nak ambil 2 desimal boleh je, tak ada masalah. Okey je, 0.48 pun okey, no issue. Okay, so actually you can cross check, okay, your answer by using the table. Okay, so the second question here is try to find this by using the shortwave table, okay, and then make sure you get the same values lah. Okay, so I think M1 you cannot use the table lah. M1 ni you have to calculate, okay, because you are given with the V1s 1000s. So once you get M1, so use table to find what is the M2, what is P2, and what is T2. Okay, and density pun sama. You cannot find this from the table lah. Okay, pressure mark number 2 and temperature 2, so you can use table and please cross check. Okay, so the values or the answer will be plus minus with what you get by using this equation. Okay, all right, so I think the rest is quite similar. Okay, it's very simple actually topics. Okay, for me it is basically a bonus question for you in final exams. Okay, okay, let us do one past year question. Past year questions. Okay, so A, briefly explain the formation of the shock wave in compressible flow and its properties across the normal shock wave in terms of pressure and temperature. Okay, so I think this one you should be able to explain, right? How the formation of shock wave and what will happen, okay, to the pressure and temperature when it cross the shock wave. Okay, it will experience drastic increments. Okay, with the pressure, temperature, as well as the entropy. Okay, and then for question B, okay, try to do this question B. A bullet released from AK-47 rifle travels at a speed of 460 meter per second, causing a normal shockwave and passes through stagnation air at a pressure of 100 kPa and temperature of 15 degrees C. So by using the table, determine okay, the Mach number before the shockwave, after the shockwave. This is similar questions, okay, with what we did just now. Okay, temperature, velocity after the shockwave, and density after the shockwave. Okay, try to do this one. Use table. I will share the these questions. Okay, later on. This question you have to interpolate. Okay, you have to do the interpolation lah. Okay, so here is the answer, mark number 1 before the shock wave. So what is mark number 1? So my answer is 1.35. Okay, please double check. Okay, 1.35 mark number after the shock wave, and then you use the tables, and then you need to do the interpolation. So I got 0.7628, and pressure after the shock wave. This one also you have to do the interpolations. My answer is plus minus, right? kPa, and then temperature is around 352 kelvins, and the velocity is about 286.9 meter per seconds, and the last one is the density. It's about 1.94. So this is the answer. So please double check lah. Okay. And is it possible for the normal shock wave to occur in a subsonic flow? Okay, the answer is not possible lah. Okay, because when you convert subsonic to supersonics, it means that your entropy will be decreased, okay, which is impossible to happen. Okay, so that is the answer for this question. Okay, ada soalan tak? Any other questions? Okay, so if you don't have any question, I think that's all for today. And we officially completed this chapter number 4, compressible flow. So we have covered the isentropic flow as well as the normal shock wave. Okay, and I think tomorrow we are going to start the last chapter, number 5, okay, which is the turbo machinery. Okay, everyone, I think that's all for today. Thank you for coming. I will share the QR code for the attendance in the WhatsApp group after this. See you tomorrow.
Doktor,
Yes.
kalau macam kan dia 1.35 kan.
Hmm.
So basically di antara 1.34 dengan 1.36. So kalau setiap ni macam saya tak interpolate tapi saya tambah 2 bahagi 2 boleh ke?
Boleh je.
Tak
masalah.
Tapi ada yang lain sikit lah, sikit. Ada yang sama, ada yang lain. Tak tahu kenapa.
Dia plus minus lah sebab dia ada decimal point kan.
Oh, okay.
Ya.
Okay, thank you, Dr.
Okay. Okay, thank you everyone. See you tomorrow.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.